All right, hey everyone, we are on to our next video. This is video 4.4. This is all about osmosis. So if we remember from our previous video, we were looking at how we can how certain molecules can diffuse in and out of the cell. And so this particular example, osmosis, is focusing on the diffusion of water. So that is what our primarily focus is how water is going to move in and out of our cells. So here we have our definition of osmosis is the diffusion of water across a selectively permeable membrane. So remember that a selectively permeable membrane is referring to a membrane that only allows certain things to move in and out of the cell. So it's selective. Okay, so what we want to look at, it's kind of blocking there. If a membrane is permeable to water but not to a solute, it separates the two solutions with different concentrations of solute. So water will cross the membrane, moving down its concentration gradient. So it wants to move from the high concentration of water to a lower concentration of water. And then it wants to have that equilibrium on both sides of the membrane. So let's look at this image. So we have this image and it asks, is osmosis a passive or active transport, and how do we know that? So like what it was just discussed in the previous slide, water is going to move with its concentration gradient. It's going to move from a high concentration to a lower concentration. So what do you think? Is that a passive transport, or do you think it's active? So the answer is it is a passive transport because it's moving with its concentration gradient. And so we can see that, yeah, it is passive because it moves from high to low, but you have to remember that water is a charged molecule. It's a polar molecule. And so, yeah, it could move through the cell membrane. It could move by itself, but it's just really slow to move through the membrane. So we have these aquaporins that are these protein channels that allow the water to move in and out of the cell very quickly. So this is really an example of facilitated diffusion. So here is just a reminder that molecules can cross the membrane without the help of any proteins, without any energy that's necessary. And these are typically the molecules that are nonpolar and they're very small. So they don't have a charge and they're really tiny and they can fit through that membrane. Things like oxygen, hydrogen, carbon dioxide, those are the things that actually can move through our phospholipid bilayer without any help and without any energy. But because water is charged, it's polar, it needs a little help from an aquaporine to make it much faster. So here's an image looking at if we have some solute concentration over here, right? These little purple dots are solute. And a reminder, what is solute? Solute are things that can be dissolved in water, typically water. Like salt is an example of a solute. Sugar is an example of a solute. And we usually use those two examples the most, salt and sugar, for this particular section. So we have our concentration of water and we have a concentration of solute, which we want to keep in mind as we kind of go through some of these practice problems that you'll see on the next few slides. But remember that when we are looking at this movement across the membrane, we always want it to be in equilibrium, or it wants to get into equilibrium. So if we're looking and we're primarily focusing on water, right? Osmosis is the movement of water. So what's going to happen to the water that's over here and over here? So when we look, there is a much higher concentration of water on this side. Because there's a low concentration of solute, that means that there's a higher concentration of water. And water always wants to move from high concentration to a lower concentration. And we can see that happening when we look from this image to this image. We're seeing the movement of water from this side to the other side, and actually now we're seeing there's an equal concentration of water and solute on both sides of it. And so this membrane is actually selectively permeable, and it only allows water to move through the membrane. And this image is a blown up image of what's happening above, is that only the water molecules can move through this semi-permeable or selectively permeable membrane. And it actually allows for this equilibrium to happen for both sides. So this is osmosis, is the movement of the water molecules. So in order for organisms to live, there has to be a balance of water. Too much water is not good, not enough water is not good, and so we kind of look at these different scenarios. So water balance between cells and their surroundings is very, very important to our living organisms. So tonicity actually is the ability of a solution to cause a cell to either gain or to lose water. And there are different solutions that we're going to look at that will really kind of depend or show us if the water is going to move into the cell, is the water going to move out of the cell, is it an equal concentration of both sides so that the water stays the same on both the inside and outside. So here are our three solutions. We have an isotonic solution, a hypotonic solution, and we have a hypertonic solution. So when we're looking at our different types of solutions, let's go through each of these examples. The first example is going to be a hypotonic solution. So a hypotonic solution is when there's a lower concentration of solute on the outside. So a low concentration of, let's say, salt or sugar on the outside, which means that then there's a higher concentration of water on the outside of the cell. So it's in a solution where there's not that much solute, but there's a high amount of solvent, which is our water, and so that means that the water is going to move from a high concentration to a low concentration, which is then going inside of the cell. And it actually causes our cell to expand or even lyse. Lyse means to burst or explode. Then we have our isotonic solution where we have equal amounts of water on both the outside solution and the inside solution. So inside of our cell, we have the same amount of water, so it's in equilibrium already, and so water would just move in and out of it, but at equal rates. And then we have our last solution where we have a hypertonic solution where we have a high concentration of solute on the outside. So we have a lot of sugar, a lot of salt on the outside of our cell. And because we have a high concentration of solute, that means we have a low concentration of water on the outside, which then means on the inside of the cell we have a high concentration of water. And how does our water move? It always moves with its concentration gradient. So it's going to want to move from the high concentration inside the cell to a low concentration outside of the cell. Water moves out of the cell, and that actually causes the cell to shrivel up and typically to die if it doesn't have enough water. And here are the definitions of each of those, so you can pause here and read through them a bit more, but we just went over the definitions on the previous slide, so you can read through those yourself. So here, though, it's important to recognize that animal cells and plant cells are going to be most successful in different types of solutions. So for an animal cell, being in a hypotonic solution where there's less solute on the outside and more water on the outside, and that water moves into our cell, it causes the cell to expand and to burst. So that's not good for animal cells. What's the best for an animal cell is actually an isotonic solution so that it stays the same size. So there's equal amount of water inside and outside of the cell. Hypertonic, also not good for animal cells because water will move out of the cell. This is like when it's like a really salty solution, for instance, and so and there's a higher concentration of water on the inside, and so it actually tries to create this equilibrium and water will leave the cell. But for a plant cell, it's actually quite different, where the best environment for the plant cell is actually in a hypotonic solution. So when we have a low concentration of solute here, but a high concentration of water on the outside, water will move where there's a lower concentration inside the cell, and that allows the cell to expand. And because a cell has a cell wall, it prevents the cell from bursting. So it prevents it from getting too big. But we want the cell to be, it's called turgid, where it's being pushed almost like a balloon, it's being blown up, but not too much where it's going to explode because the cell wall is there to prevent it. But because it has the water, it pushes on the cell wall and it helps the plant stand up straight. If it's in a isotonic or a hypertonic solution, it's not getting enough water, and so that's why those plants will kind of flop over. There's not enough water in there to push against those cell walls, so it just kind of flops. So those are the differences between our animal cells and our plant cells and what kind of environment is better for them. So now we're going to go through a few examples looking at how water is going to move in and out of cells in different solutions. So we're always going to be referring back to, we have a red blood cell that contains 95% water. And then we're going to put the red blood cell into different environments and see what happens to the cell. Is water going to move into it? Is water going to move out of it? What's going to happen to the cell? So please follow along with me with your drawings. This is the scenario that we're going to be focusing on. And whenever we're doing these types of drawings, it's a good idea to put it into, I like to put it like into a beaker almost, or just to have this idea that it's in an enclosed area. So I like to draw the red blood cell in the center here. So there's my red blood cell, and we're looking back over here, right here, and the red blood cell has 95% water. And we need the total amount of material inside the cell to add to 100. So how much solute is in our red blood cell? Well, we just do 100 minus 95, and that gives us 5% salt. And really, you could put solutes, either way is fine, but that's what we're going to do. 95% water, 5% salts. And we're putting it in a solution where it's 100% deionized water. So 100% water, 0% solute, right? So what's going to happen to the water, right? So we have to remember that water is always going to move from a high concentration to a lower concentration. So water, which is higher out the outside of the cell, will move inside of the cell. So what's going to happen to the cell? What happens to a red blood cell? Well, the red blood cell will actually either expand, and there's the potential that it might even lyse, and lyse means to burst. So what type of solution was our red blood cell put into? What kind of solution is this? This is called our hypotonic solution. Hypotonic solution, where there's less solute on the outside of the cell and there's more water on the outside of the cell, so the water is going to rush to the inside of the cell. All right, so that's our first example. Let's go to our next example. I guess I got to erase all this. Okay. All right, so our next example. We still are going to have our same red blood cells. So same thing, 95% water, 5% salt, right? We got that right from the top, the same scenario. But this time we're putting it into a 5% salt solution. So NaCl, that means salt. Right, like that's table salt. Okay, so we're putting it into our environment. Our solution is 5% salt. And then how much water does that mean? Right, it has to equal a total of 100%. So we just do 100% minus 5, and that gives us a 95% water concentration on the outside of the cell. So we see here, okay, well, this is, once again, we're talking about osmosis, and osmosis is focusing on the movement of water in and out of the cell. So if we have the same amount of water on the outside as the inside, then water will move in and water will move out at the same rate. So it's not going to change size. So the cell will stay the same size. So cell stays the same size, it's not going to expand, and it's not going to shrivel up. What type of solution is this? Well, if it's an equal amount of solute on the inside and the outside of the cell, this is an isotonic solution. Oops, this is an isotonic solution. Okay, so that's that example. Make sure you have that down. Let's move on to our next example. All right, so it's the same idea with our red blood cell, right? 95% water and our 5% salt. or NaCl, same thing. But let's see what's going on with our the solution here. So it's 5% salt, which means how much percent water? 85% water. So now we got to look at our concentrations of water. Where's the water going to go? So remember, water will always move with its concentration gradient. It will move from high to low. So because we have a higher concentration on the inside of the cell, 95% versus an 85% on the outside, water will move outside of the cell. So that means that this red blood cell is going to shrink, or it's going to shrivel up. So it's going to get smaller. What is the solution like? So remember, this solution, there is a high concentration. There's a higher concentration of our salt. So that means that it is going to be a hypertonic. A hypertonic. Sorry, that's kind of hard to read. That says hypertonic. So this is a hypertonic solution because there's a higher concentration of solute outside of the cell. Okay? All right, and then we have one more example to go over. All right, last example. I'm focusing on that red blood cell being 95% water. And it's always a good idea to write it out, draw it out, even if you feel like you can do it in your head. Sometimes you lose track of numbers, so it's always a good idea just to draw it out. Okay, so now we're looking at a solution where there is 1.5% salt. And now we want to think about, what is the water concentration here? So we have a 98.5% water concentration on the outside of the cell. So even though the concentrations of water are similar, there's a higher concentration on the outside of the cell. So water always wants to move from high to low, and so water is going to move inside of the cell. So what will happen to the cell? It's going to expand, maybe not as quick as the other example that we went over when the cell was expanding, but it will still expand, and could eventually lyse. What kind of solution is this? So because this solution has a lower concentration of solute outside of the cell, this is our hypotonic. This is our hypotonic solution. Okay? All right, so that's that example. Here's our last one we're going to go over together. It's our final example. So we have a cell that's has 85% water is placed into a solution with 15% salt. So once again, you always want to just draw it out. So if this is our cell, let's just say this is our cell. So we have 85% water. How much salt is going to be on the inside of that? Right, we just do 100 minus 85, that gives us 15% salt. Then we want to look at, okay, then it tells us that our solution is 15% salt. Okay, so that's the first thing we'll write down. Okay, there's 15% salt. Oops, that's not right. I almost wrote water. 15% salt. How much water would that be? 85% water. Okay? So we can see right away that the concentration of water on both the outside of the cell and the inside of the cell is exactly the same. So we would just draw that in there, but it doesn't matter. Just showing that water is going to move both in and out of the cell, and that results in what type of environments here. So let's look through these questions. So it says, what passive transport will allow for the water to move between the cell and the solution? So what kind of transport allows for this? Now this is called a facilitated diffusion, right? This is facilitated diffusion because in order for the water to move, I mean, water can move through the cell membrane without the help of a protein, but typically it uses a protein to go through, using the aquaporin to go through it. So facilitated diffusion, always moving from high concentration to low concentration, typically with the help of a protein, the aquaporin. So which direction will the water move? The water moves in and out. So we could say it moves in and out of cell, okay? The cell, what's gonna happen to it? Nothing, it's gonna stay the same. So it stays the same. The size is not gonna change. And then what kind of solution is this? This is an isotonic solution. So isotonic solution is when there's equal concentration of solute inside and out of the cell, and so water will move in and out of the cell at equal rates. All right? Okay, so that is all about our osmosis, and looking at tonicity is really focusing on the movement of the water in and out of a cell when it's placed in different types of environments. All right, so I hope that was helpful, and if you have any questions, just let us know. Have a great day. Bye.